Hi, this is Mrs. Hammer, and we are going to be talking today about the structure of the atom. And since this is a pre-AP chemistry class, this will be a lot of review. So we're going to go through some things very quickly, and then I'll slow down on things that I think might be brand new to you. So you can follow along in your notes starting on page 3. And I have a cold, so please forgive me for coughing. The major parts of the atom, we're going to start out with this. The major two parts of the atom are the nucleus and the electron cloud. So the nucleus is the very, very, very dense part of the atom that is right smack dab in the middle. This picture here is actually a terrible picture. If I can point to something for you, the nucleus here indicated by these protons and neutrons are actually much, much, much smaller in comparison to the atom as a whole. The analogy that we've given is that if the atom as a whole was an entire football stadium, so like a gigantic football stadium, the nucleus would be the size of a bean sitting on the 50-yard line. So it's very small and it's very, very dense. And the electrons would kind of be like mosquitoes buzzing around. So again, this is the nucleus, and it has protons, which are positive, and neutrons, which are neutral, of course. And then the other part of the atom is called the electron cloud. And again, this picture is pretty terrible because it makes it seem like there's just these few electrons right nearby the nucleus. Instead, the electron cloud is a very, very large area that at any given moment in time is mostly empty. So the electron cloud would be like the full volume of the football stadium. And the electrons are like the size of mosquitoes just buzzing around. So the electrons live or occupy the electron cloud, and it's very, very large in relation to the nucleus. So here's just a review of the parts of the atom. So our protons are here in the nucleus. They have a positive charge, and it says relative size is large. That is in comparison to electrons. None of these things are really large. This is just in comparison to each other. So the protons are relatively large, just like the neutrons. So they're actually very similar in size. The neutrons, of course, are neutral. And in the nucleus, we saw that in the picture, the electrons are in the electron cloud. They are negative in charge, and they are very, very tiny. So we need to talk about the periodic table. Most periodic tables that you're going to see only have 2 numbers on them, and we need to talk about what those numbers mean. You may have actually been lied to in the past. Someone may have told you that let's look at copper, for instance, that the top number is the number of protons, and that this number down here is the number of protons plus neutrons. So you may have heard that in the past. And that might appear to make sense for elements like oxygen and fluorine, where the number is 16 or 19. That could be the number of protons and neutrons. But for copper, 63.55 is your teacher claiming that you have 0.55 of a proton or a neutron? That's like half a proton or half a neutron? Not really. So this bottom number down here is something different. And so we need to talk about what these numbers mean. So first off, the atomic number is the whole number or the integer number on the periodic table. Okay, the atomic number. The atomic number equals the number of protons in the atom, which is what you probably have learned, so that's still true. It also equals the number of electrons in the atom, assuming it's a neutral atom. The protons and the electrons would be the same. So if we take an example and we look at potassium, it says the atomic number for potassium is, so we want to look back at the periodic table and find potassium. Potassium is up here, okay? And again, the number up here, the integer number, is the number of protons. So for potassium, it's 19. So the atomic number is 19. So that also means it has 19 protons and 19 electrons. The atomic number is truly the identity of an element. If you change the atomic number, somehow you're changing which element it is, okay? So if we take the 19 and we change it to atomic number of 20, it's no longer potassium. Let's see, that would be calcium, because calcium has an atomic number of 20. So every atom on the periodic table has its own unique atomic number. Next, another example, chlorine. We want to look up the atomic number of chlorine, so check out your periodic table. We see chlorine over here in the halogen group, and it has an atomic number of 17. It's the integer number. So it's an atomic number of 17, therefore it has 17 protons, and it also has 17 electrons. Again, the protons and electrons have to be equal so that it is a neutral atom. All right, another way we could think about this, an atom has 24 protons. What element is it? So again, the protons equals the atomic number. So we just find the element with number 24. So it looks like that would be Cr right here. Number 24 is Cr, so it's chromium. Chromium. Here we go. Another number that we sometimes think of, and this is what your junior high teachers probably talked to you about, it's called the mass number, and it is the sum, which means add, the sum of the protons and the neutrons, okay? This number actually isn't on the periodic table, and this is where you may have been lied to. It was with good intentions, I promise. This number isn't on the periodic table because any given element could have a wide variety of numbers, of mass numbers, okay? So these varieties are called isotopes. So for instance, we might have carbon, which has 6 protons, but one version might have 6 neutrons. Another version might have 8 neutrons. So they can have different mass numbers. So there simply are too many of those to label for each element on the periodic table. So again, for carbon, it has a number, 12.01, but that is not necessarily the sum of the protons and neutrons. So we have to get it out of your heads that this number down here is protons plus neutrons. It's simply not true. The number that is on the periodic table that you've looked at in the past, that's called the atomic mass. Sometimes it's called the average atomic mass, AVG for average. The average atomic mass is the decimal number on the periodic table, and the average atomic mass is the average mass of all the isotopes of that element. So again, carbon exists as several different isotopes. Carbon-12, carbon-13, and carbon-14 are just a few examples. All of those averaged together give us 12.01, and that's called the average atomic mass. Now, you may know a little something about averages, and you may know that the average of 12 and 13 and 14 should be 13. So why am I telling you it's 12.01? There's more to the story. It's called a weighted average. Basically, most carbon in the universe is carbon-12, so we kind of count those more. So the average ends up being closer to carbon-12. We will talk more about that on another day. So for now, just know what the number is. It's the decimal number on the periodic table. Again, for carbon, it's 12.01. For copper down here, it was 63.55. And that number simply represents the average mass of all the isotopes. Okay. Again, isotopes are atoms of the same element that have different mass numbers. So this means they have the same number of protons, but a different number of neutrons. So my example earlier for carbon-12 and carbon-14, they each have 6 protons, but carbon-12 has 6 neutrons. The abbreviation is N with a little O up above it, whereas carbon-14 must have 8 neutrons. So again, here's an illustration of those isotopes here, okay? So carbon-12 over here still has 6 protons because it is carbon, okay? But it has 6 neutrons. So when we add the 6 protons and neutrons together, we get that mass number of 12. That's one version of carbon. Another version is down here. We have 6 protons still, but the neutrons are 8 this time. So it's just a different variety. And so, of course, 6 plus 8 is 14. So it is carbon-14. That's the name of the isotope. Okay. The most common element in the universe is hydrogen, and it does have 3 different isotopes. And so we do expect you in pre-AP chemistry to learn the names of those 3 isotopes. Now, these isotopes are called protium, deuterium, and tritium. These are all isotopes of hydrogen. Notice that they all have 1 proton. So these names, protium, deuterium, and tritium, don't show up on the periodic table because all of them are this element up here, hydrogen, okay? They're all the element of hydrogen, but there are 3 different versions of hydrogen. So these are like subcategories of hydrogen. So the first one is called protium, okay? It's the first one. It has 1 proton and no neutrons, so it has a mass number of 1. So this is also sometimes called hydrogen 1. Hydrogen with a dash and a 1, okay? Deuterium is often called hydrogen 2, so sometimes called H-2 because it has 1 neutron. And tritium has 2 neutrons, so 1 proton plus the 2 neutrons equals 3 for the mass number, so it would be called hydrogen 3. So again, we do expect you in pre-AP chemistry to know these 3 isotopes of hydrogen because it's the most abundant element in the universe. So there's 2 ways that we can write down isotopes. A big thing that we do in chemistry is we try to write on paper representations of things that exist in nature, okay? So one method is called the superscript-subscript method. So I'm just going to go ahead and skip ahead, and this is an example of the superscript-subscript method. We see that the number on top 37, that corresponds to what's called the mass number. And remember that that's the protons plus the neutrons. And then there's a bottom number which shows us the atomic number, which remember is the number of protons. So we take the element symbol, we write the mass number as a superscript, that's the top number, and the atomic number as a subscript, that's a bottom number. So it's all kind of laid out for you here. The atomic number is your subscript written below, and the mass number is your superscript written above. Both of them are on the left side. So in this example here, uranium-235, the top number is the mass number, top 235, and the bottom number is the atomic number. So one thing that we can use these symbols for is we can figure out how many neutrons are there, okay? So if the top number is protons plus neutrons, and the bottom number is protons only, we would of course subtract. So I'm going to pull up my calculator here, okay, and turn it on. And we're going to do 235 minus 92. We see 143. So we would have figured out that there are 143 neutrons in this isotope of uranium. The other method is called the hyphen notation method, or just the hyphen method. Lots of people think that it's true. Lots of people recognize that it's kind of redundant for us to give the element symbol chlorine and the atomic number. Because if you know one, you know the other. So why do we need to give both? Okay, so we're going to cut one out. We're going to get rid of the atomic number, okay? And we're just going to give the element name or symbol with its mass number. So again, this is the hyphen method. You do the symbol, then a hyphen, then the mass number. So the example of uranium that we looked at earlier becomes just U-235. Again, the atomic number we don't really need to write because if we wanted to know it, we could easily look it up. For uranium, down here, the atomic number is right there. It's number 92. So going back, all right, so that's pretty much it. What I want you to do right now is you should have this table here in your notes. I want you to pause the video right now, and I want you to do your best to fill in the information that goes into this table, okay? So again, you're going to fill in the atomic number, the mass number, the protons, the neutrons, the electrons. This is the superscript-subscript method, and this is the hyphen method. So go ahead and pause the video and fill in what you can, and then I'll move on and I'll show you the answers. All right, so here we have the completed table. Again, you should pause the video here and check your work and see if you made any mistakes and try and correct them. All right, so that is it. That's our review of the structure of the atom and isotopes. So your homework is page 15 if you are in Mrs. Hammer's class in the year 2016. If you are not in Mrs. Hammer's class in the year 2016, you should check with your teacher because it might be something different. So I hope this video was helpful, and I'll see you again in another video. Have a good day.